And if we think about calculating characteristic length for this, so it's volume, and I'm going to give some dimensions here. We're going to call this an L, and we'll make it 2L thick. So if I'm calculating volume, I have 2L for my thickness, and we're going to put some surface area in here. Oh, sorry, that's not where I put my 2. Sorry. Okay, just some surface area. So 2L thick, and I got a surface area. All right. In the denominator, we want to think of what surface area is exposed to convection. And we have 2 faces being exposed to convection. So if I was calculating my characteristic length, in this case, it would be half the thickness, or L thick. Okay. If I had an insulated boundary over here, we would go through the same exercise. Now the volume is going to be L times surface area, but the area that is exposed to convection is just 1 surface area. Okay, we did this the other day when we talked about one-dimensional conduction in fins. Okay, but we're thinking of this Biot number as a ratio of resistance to conduction, and because we want this to be a small number, we want that to be small, and we want resistance to convection to be relatively large. Okay. And if you think about where this Biot number comes from, resistance to conduction, it's an L over Ka. If we think about the wall, and resistance to convection is 1 over Ha. And it's the same surface area, and I can rearrange this to look like so it's easy to think about what this resistance looks like for the plane wall. We will talk about, again, this characteristic length. We've already got our definition for how we calculate that. All right. Dang, I have a really cool picture in my notes. You guys don't have it. All right. I want to do a little bit more discussion about Biot number. All right, this is a bunch of cars on an island. Okay, and we got boats out here. Okay, for lumped capacitance to be valid, we would like to think that on this island we have really good car transportation. And not so good boat transportation. Okay. And the idea is, if you think about people on this island are like packets of heat, that if I'm, a few people get off on the boat over here, I'm able with this good vehicle transportation, with this good on-land transportation, to smooth that out. So I get uniformly distributed people or packets of heat. So really uniformly distributed. And then maybe some people leave over here, but I have really good transportation. Now, if I had really good boat transportation and a whole bunch of people left over here, I'd have trouble shuffling all those people by vehicle transportation. Okay, I don't know what you think about that analogy, and I have my little note in here. I think Larry Miller still works at GEA. Does anybody know Larry Miller? No. Okay, he hated this analogy. Okay, and all it was is to get you thinking about, again, really good car transportation, that's really good conduction. Not so good boat transportation, that's that we want convection to not be so fast that I'm pulling heat out of one side or the other. All right, and last thing I'll say about this is you can see through all of the things. Again, we don't want a super high heat transfer coefficient. We don't want a really large body, so we don't want characteristic length to be too large. And we would like a large K. So a lot of times we do these ball bearing problems. You know, you think of metals having high thermal conductivity, pretty small, so they have low characteristic lengths in order to be able to apply lumped capacitance. There is a general setup for lumped capacitance problems. And at least when I taught lumped capacitance in the undergraduate class, we talk about convection only. So we got this chunk of material, or we've got a sphere or cylinder, and all we have is convection going on. That's one of the cases, and it's a useful case, but we really can do more problems than that. So this setup, and your book starts this way, is to look at this general lumped capacitance. And so we've got our energy balance equation on a rate basis. And then what they show is what I might have coming in. This is kind of tiny, but here's a heat flux. And they show that this is surface area for the heat flux. And they're kind of particular about showing I don't have to have heat flux on all surfaces. They've only showed it on one of the walls. It doesn't apply on the other wall. We could apply it on both. They're just trying to show a general situation. And then convection. Okay, so we're used to that H Ts minus T infinity. And they're showing that on our particular surface area. And it might be different. It might be both faces. It might be a single face. They show radiation occurring, and they are careful to say, I might have radiation on both faces. We'll just use this precise surface area on which radiation occurs. And they've shown both of these with negative signs just to go with our picture. We could have radiation in or radiation out. We can handle volumetric heat generation, and then the storage term is shown as sensible heat storage. Okay. So we have a temperature change. We can't handle the phase change yet, and that would be that I put this heat in and I don't see any temperature variation. I just see a phase change. We're going to consider a sensible heat change. This is a nonlinear, first order, non-homogeneous, ordinary differential equation. Okay. And there are special cases that we will talk about solutions for this. Okay. So the first special case is convection only. And the convection heat transfer coefficient has to be a constant value. Right? And that's the one I think many of you will be familiar with that one. And I'll spend a little bit more time developing some equations for this case. The second case and it's listed in your book, they give a solution, and I don't plan to go through this one. It's radiation only. So picture I have some object and there's no convection because I've got no fluid surrounding it, but I've got a vacuum and then there's a T surrounding. And so there is and you want to imagine, so this is transient again. You have some object, it's at some initial temperature. You suddenly put it in this vacuumed situation, and you know a surrounding temperature. You can figure out, at certain length of time what its temperature is, or the other direction, if you want to know how long it takes to heat this up or cool it down. You can solve for if you know the initial temperature and the surrounding temperature. Oh, and actually, this equation, as I think about it, I think it's written explicitly to solve for time. So the easier way is if you know an initial temperature and surrounding temperature. I think this is a pretty unusual case. I'm trying to think of situations in practice where you'll use this, and we don't have so many cases where we're working with a vacuum. Third one is negligible radiation. Okay, so if we go back to this equation, we're dropping out this term, but we're able to handle volumetric heat generation, convection, and a heat flux, applied heat flux. So this one seems pretty all-purpose, and we'll spend a minute looking at that one. And then the fourth one is convection with a variable convection coefficient. All right, so up here, H has to be a constant. Here, we allow H to be a function of a temperature difference. All right, so this one I think is useful, and I know I will talk about this a little bit more in an upcoming lecture. This one is usable for free convection. So if you think about, if we know the velocity of air over a surface, or if we know the velocity of fluid, whatever, and we have a constant heat transfer coefficient, this one is going to be easier to use. We know at H. But free convection, that's when it is buoyancy driven, and it has it is based on the difference between the object's temperature and the free stream temperature, and that's going to keep changing. That is not going to be a constant. So this fourth one, it's kind of interesting, I think, for looking at free convection. If I scrolled up and looked at that general equation that is 2 slides ago, right, we're considering I could have convection on the object. I'm not having a heat flux. I don't have radiation. I don't have volumetric heat generation, but then I have a temperature change with time. So I'm allowing the transient effect. So we're going to let theta equal T minus T infinity. So my equation now looks like we're going to reorganize this equation. let's see, and I put dt on one side of the equation and everything else on the other side. So dt over here. Okay, and you're probably guessing what I want to do next is I want to integrate, and I'm going to say from t is 0 to some time, and I'm going to integrate, and this is theta I is an initial temperature minus T free stream. And I'm going to go to theta final, which is the final temperature minus the free stream temperature. All right, so I'm just going to write this as the time sorry. Let's get our natural log in there. Okay, so a couple things I can do is I can absorb this negative sign. So I'll have natural log theta I minus theta final. And rather than writing this as the difference of natural logs, I will write it as the natural log of a ratio of these thetas. Okay. This is a form of the equation. I would say most often you're either solving for the time, or if I wrote this guy out again, or solving for a final temperature. I mean, you're almost always given initial temperature at T infinity. Okay, so two ways we can work with this equation. You know, I should be listing some assumptions. Okay, so we're no longer looking at steady state. So we know it's transient. And then the other thing, a lot of times we'll say one-dimensional conduction. Well, we're not assuming that either. This is really zero-dimensional conduction. As long as it behaves as long capacitance. We do need to check that. We are assuming constant properties. You know, I'm going to add explicitly that H is a constant. And I'm going to add that heat storage is sensible heat storage. Okay. All right. I had in my notes to mention this, so let's. You know, I said convection only here. Okay. There are sometimes problems where they're going to tell you the combined convection and effective radiative heat transfer. So H, let's say convection plus H radiation is some H combined. So if I knew that was relatively constant for a period of time, I might still use this case one equation. If this is nearly constant and we're still using this thing that says convection only, it's the idea that I really want heat transfer coefficient that is a constant. It's not that I can't handle radiation, it's that I have to know I have a nearly constant value. All right, so this goes with these lump capacitance problems. All right, this next thing I wanted to do is show how you could calculate if I, have some, oh, yeah, one more. So when they give us some temperature for the initial case, it's uniform. So we don't have a temperature distribution at the starting point. Okay. If we wanted to solve for total heat, either if I had this wall and it's initially at some temperature and I suddenly have heat being pulled out or heat added, I could go either direction. And so now it's not a rate. I want to say over 5 minutes, what's the total amount of heat I remove from that wall? So I like you thinking it would have units like joules or kilojoules. Okay, so total heat transfer is going to be integrating the rate of heat transfer, so that little q, over time. Okay. And I'm going to replace this rate of heat transfer with a convection, like a Newton's law of cooling equation. So a heat transfer coefficient, a surface area, and T minus T infinity. And we're so used to, I almost did it. I almost put the little S there, surface temperature. And it's not that we don't want the surface temperature, but I would like you thinking that this is not a constant value. So now we're doing a transient problem. That temperature is varying. So I'm going to get rid of that. Okay. All right, so if I want to come up with this integral, I can go ahead and take H and AS out of the front, but T, and again, it's going to be a function of time minus T infinity. I need to do some more work in order to integrate that. Okay. So I'm telling you, I'm saying recall, but let's scroll up for just a minute. Okay. If I took all of this stuff to the other side of the equation, and then I took the exponent, so I get rid of my natural log here. Hopefully this equation looks like a rearranged version. Okay, so this comes from lumped capacitance assumption. And then reminding you that this theta, that's temperature changing as a function of time minus T infinity over theta I is, and I'm going to leave it as a theta I, but it's initial temperature minus T infinity. Okay. And this is what we want to substitute in to that equation. All right, so theta I, and then I have to have exponent of minus HAS T over rho volume C sub P, and I'm finishing off with dt. Okay. You know, I have to remember my rule that integral of e to the u du is equal to e to the u. And so I got to form so if I make that all of that term in the bracket is u, I get exponent of u, then du is equal. All these things are constant, just my t. So I want to form that. Keep carrying this theta I along. All right. So this is okay. So I'm adding that constant because I'm going to need the reciprocal to form my du. So I'm just showing you again because I wanted to form this du. So I've got e to the u du. I have to have this constant out in front. Okay, we're getting close. All right, I got to keep this guy. Okay, and I've got an e to the u that I'm left with. And now I have to put my limits in that I'm integrating over time. So t is equal to 0 to t is equal to some final time. All right, we can do a little bit of simplification, right? I got maybe that's it for now. Okay, so I'm putting my first limit in, so I'm just keeping that as a T. Okay. Minus, and now I have this T is equal to 0. And that just goes to 1. Okay. So the last thing I want to do is get rid of this negative sign. So I'm going to multiply it through at theta I, rho volume, C sub P, 1 minus exponent minus HAS T over rho volume C sub P. Okay. And we did all that work. I want to be thinking about the fact that that gives me total amount of heat. So joules or kilojoules that were lost over some length of time that this object was exposed to a convective boundary condition. And I haven't, we're used to seeing density. I've been using this symbol for volume. Okay. I'm a little bit shaky. Sometimes I use the C sub P and sometimes I get going or reduce it a little bit and use just a C, but CP is specific heat. Okay, I am showing you this equation, but I'll tell you, it's always bugged me. And this equation works fine, But let's say I had, I don't know, let's make it a sphere, something easy. And we know its initial temperature. Let's say it's given. Okay. And let's say it cools to a final temperature. If I had to find the total amount of heat loss, because there's no variation spatially, I can solve for the total amount of heat loss by rho volume C sub P, T final minus T initial. Okay. So I think there's times when this equation is like overkill. It's useful for some stuff we're heading towards, but a little bit overkill for this zero-dimensional transient conduction. Okay. We're going to do a quick calculation, and this is going to be a type 1, the one where we have just a constant value for convection. So it says springs for a suspension system need to be wound while ductile. Consider steel rods, and they tell us the big 3 properties with a diameter of 2.5 centimeters and length of 1.27 centimeters. The rods start at a uniform temperature of 20 degrees C, so they're cool, kind of room temperature, and desired temperature is 450 degrees C. The rods stay in the furnace for 10 minutes with a convective heat transfer coefficient of 20 watts per meter squared Kelvin. Okay, and we're supposed to find what the temperature in the oven. This would be in our symbols a T infinity, so what our free stream temperature is. We assume constant properties. We're ignoring any radiation. So this is in air, and I would say ignoring radiation in an airstream. We might want to think about that, but we're going to make that assumption here. We think that lump capacitance is going to be what we're going to use because we just talked about it. But let's check it. And for some reason, I like to do this as a side calculation. We know heat transfer coefficient, right? Where is it? 20. And we know K. And we're going to use our general definition, volume over surface area. So we've got this, where does it tell us? Diameter of 2.5 centimeters and length of 1.27. We're going to say we have this quite long rod. So volume, pi d squared over 4. So that gives me cross-sectional area and then my length L. And surface area is going to be pi dl. All right. And let's make a note. Okay. I am leaving off these little surface areas. Okay. For this length. You know, and I didn't calculate it. We could put it in and see how much difference it makes, but it's a pretty small difference to consider that. So let's add another I'm ignoring any heat loss from the ends. Okay, so the only surface that I have convection removing heat is the cylindrical surface. My diameter is 2.5 centimeters. And K is 63.9. All right, and I can already think through. I've left off a unit here. So I need in the numerator should be watts per meter squared Kelvin. Okay. So this is a tiny number. Our cutoff number was to have it less than 0.1. We've made that. We are asked to solve for the air temperature in the oven. Okay, the form of the lump capacitance equation that I wrote down looks like and if I start stepping through things, I'm going to scroll back up and remind myself. So the rods start at a uniform temperature of 20 degrees C, and the desired temperature is 450. So that's my T final. I know both of those things. And I have geometry information and properties. So I know values to substitute in. So I'm going to give these guys checks. And the only, I don't know, kind of interesting aspect. Wait, we need one more piece. Where's time? The rods stay in the furnace for 10 minutes. All right. Okay. So we know everything else except for that T infinity. The fact that it appears in two places makes you do a little bit more work. Okay. One thing to mention, characteristic length gave us volume over surface area. So it may be easier rather than going through that calculation again. I could put rho d T sub p over 4h. And the natural log. All right. I did not do a good job of showing you all these inputs. I've got this value calculated. If I put rho, diameter C sub p over 4h, I get 106.2.5. And this has units of seconds. And the natural log, this was 20 degrees C minus T infinity over 450 degrees C minus T infinity. Okay. And then on this other side, the time was given in as 10 minutes, but to keep my units consistent, I'll put it in as 600 seconds. And I can solve for T infinity of 100 or 1016 degrees C. Okay. This slide is showing convection only, lump capacitance has to be valid. So just like that problem we solved. And then the other thing that I probably don't talk about this very often, but we had a step change in surface conditions. So that was the case. We had that rod at some temperature. We all of a sudden put it into a furnace that has this hot air blowing over it. So we have a step change in boundary conditions. And here is another way to write the equation that I have previously been working with. So this would have been theta I for me in my notation. Okay. And the other thing that gets added is a thermal time constant, is this combination of terms, rho volume over, here it's a C, but hopefully you're still thinking specific heat, over heat transfer coefficient times surface area. So it makes this equation look pretty clean and neat to introduce lumped capacitance, or this thermal time constant. I like that you're thinking it has units of seconds. or some time units, whatever units you put up here, so that we get that ratio having no units. Okay, and then let's see. This graph is showing temperature versus time. And this blue line is showing that's my step change in ambient temperature. And that the object temperature, so this is temperature of the object, is exponentially increasing, and it's getting closer and closer to the ambient temperature. And I think that is one you have seen before. Here it is. Okay, I thought I wrote something about this. I've always liked this. Some people have this idea that within, and sometimes people use 4 or 5 thermal time constants, I am close enough to the ambient temperature. So for example, using thermocouples, you got this thermocouple, you stick it into some air temperature. How soon am I measuring the temperature of that airstream? And let me see if I can show. So all right, and really all I've done there is rewritten that equation. But let's say if T is 1 tau, then this ratio then this ratio T minus T infinity over Ti minus T infinity is equal to 0.368. If T is equal to, and I just did a couple, what did I do? 3 tau. That ratio is 0.05. And if T equals 5 tau, this ratio is 0.007.
Can you repeat what those numbers mean? What does the 368 represent? Is that the
3 tau, 1 tau?
Oh, is that the exponent evaluated?
Okay. So we're replacing. So for example, this first case would be T minus T infinity over Ti minus T infinity is exp. And then I'm going to put minus, it's really just 1 tau over tau.
Okay, so this goes to 1. The exponent there.
Yes.
Gotcha. Okay.
All right. And the idea is I'm getting closer and closer. This ratio is getting really close to 0. So it means this temperature of the object, so this is that's the thermocouple bead. I'm trying to measure the air temperature. It's getting really close to T infinity. It's very small error when I've gone, I'm pretty far off at 1 time constant. I'm 95% of the way there when I have 3 time constants. And I'm 99.3% of the way there when I get to 5 time constants. All right, and I guess I started out because what was I trying to go? Some people remember that feature, and I've been impressed. I guess I know it now too because I've remembered it. But that in the ballpark of 3 to 5 time constants, you should have reached your thermocouple. If it's time constant and you go 3 to 5 of those time constants, you should be measuring what you expect. You're getting very close to the air temperature. Okay. Okay, and I've messed up my notes a little bit, so I have to keep picking through. And I don't know how I did this, but here it is. Okay, I'm there. So this next case is showing still lumped capacitance. So you want to be imagining lumped capacitance is that I can change temperature of this object as a function of time, but throughout that object, I have a uniform temperature. And now we have an oscillating ambient temperature. So if you had a, okay, well, the classic example is thinking about temperatures during a sunny day. And if you look at, it's modeled as being sinusoidal, that it's like 3 o'clock in the afternoon that the ground has heated up the most, sun's been up the longest, you get a highest temperature, and it drops overnight, and it has an oscillating temperature. Okay. But the case for you guys, and could be valid, is if you have an experimental oven, you might set an oscillating temperature. So you might have it some average temperature, but you're oscillating about that average. Okay. And if you wanted to put a thermocouple probe and measure temperature, so this is going to be temperature of the object. And it is going to be equal to the average temperature. And I got a picture coming up, so let's just read through this equation for a minute. So average temperature, that this oscillating, whatever's driving this oscillating temperature, average temperature it goes through. And then amplitude is going to be half of the maximum swing. And then angular frequency is the rate at which the temperature oscillation is occurring. And the last thing that is back to our thermal time constant, and we have seen that before. So the rho volume C sub P over HAS. Okay, let's go to this next figure for just a minute. And I took these figures. Did I note early on? Maybe not. This is from a textbook by Nellis and Klein. And let me just look and see if I have. There it is. Okay. All right. This figure is also from Nellis and Klein. And I think it's a good example. This is showing fluid temperature. So this is oscillating, and this is what you're driving. You're driving that uniform temperature variation. And then sensor temperature, or I've been calling it the object temperature. But I keep thinking this would be if I put a thermocouple. To me, that's the way I can think about this is what the and originally it's got some startup time to get to its steady state oscillation. I don't know, maybe it looks like about, probably about here. We're already at this steady state. So two things that you see happen. One, because this object has thermal mass, it doesn't hit the same peak temperature. So the ambient temperature is hitting these peaks up here, but this, it's got thermal mass, so it's delayed. And by the time it hits its peak, the fluid temperature is already starting to decrease. And same thing, the object has thermal mass, so it doesn't recover temperature, doesn't mask the temperature. And then it hits this minimum, but by then, the fluid temperature is starting to heat up. Okay, so one of the features that we see, let me draw some stuff in. Okay, so let's say this is about T average. And this is delta T amplitude. So half of the maximum swing that the fluid temperature goes through. Okay. So I think of this so this is my delta t amplitude. This denominator is how much I have attenuated the maximum swing, maximum temperature swing. So this is going to be some value greater than 1. So let's say my oven is changing, half of the swing is 50 degrees C. Well, this value is going to be something bigger than 1. And so the swing of the sensor or object is going to be something less than 50 degrees C. Okay, and we saw that it's attenuated. Then this last term, sine omega t. So this is my angular frequency, so how my temperature is oscillating, but this is the phase shift. Okay. I want to go back to this picture on the next slide for a minute. So this is showing, the length of time to go through one period. And that is going to match between the fluid temperature and what the sensor measures. So that period's the same. But if you look, the peaks don't happen at the same time. Maybe I should extend upward. And that's my phase lag. I think it's easiest to think about the shift between a peak or a trough. So I don't show how you can handle the startup period, but once it hits its steady state behavior, the equation that we had on the previous sheet will allow you to calculate temperature of the object relative to what the fluid temperature is doing. And I called this a phase shift, but you can see we're subtracting it. It's really a lag. So how much we are delayed from reading the peak temperature. Okay, I think this is kind of interesting. I don't do much with this type of, this is when I have to think back, and I'm not even sure, like system dynamics or what course you would have seen this in. But I promise we'll have a homework problem, and you'll get to try out this equation. Okay, so last thing we're going to talk about is, this is again that case with convection only, and so it has to be a constant convection coefficient, and this is where the fluid temperature has a linear variation, okay, and it says a ramped ambient temperature. So if we look at the graph of temperature, and we're seeing the blue again is the fluid temperature, and this is object temperature or sensor temperature. and the object comes in at some initial temperature. And it's trying to match the fluid temperature, but it is always delayed by this thermal time constant tau. So it's always a little bit behind the fluid temperature that it wants to measure. And you can think about, if I have an object, this thermal time constant that's big, so I have a large thermocouple, I'm going to have a bigger delay. I'm going to do a poorer job of actually measuring the fluid temperature. Okay, so here it has initial temperature of the object and ambient. Okay, and then that's initially. And this is our ramp rate, beta, for how we're changing the temperature with time. Let's see, maybe I'll put this up here. So this is really the ambient temperature, or fluid temperature, right? So it's at some initial temperature and it's ramping up at that rate, beta times T. And then this part is showing how the lumped capacitance, or the thermal capacitance of that sensor, how that has an effect to further delay, make our temperature lower than the ambient temperature. I don't know, if I looked at a particular time, you get anything out of this. So I'm almost here. So that's my time difference between the two. Okay. Yeah. I know I wanted to mention that. So as time gets really, really long, this term becomes, this exponential term drops off, goes to 0. And then we got a constant delay, a constant temperature difference. So it starts out, it's pretty easy to see that I have a different delta T between them. But eventually, as I get to longer and longer times, it's a constant temperature difference between the two, ambient temperature and the object. Okay. The next thing would be looking at special case 3. All right, I don't say anything about special case 2, and I can tell you I already gave you a homework problem that's going to be special case 2. There's not much development. It's just looking up an equation in the book. But we'll spend a little time talking about this next case, special case 3. I'm going to end class for today, and as normal, I will hang out and see if I get some questions.
Thank you.
Thanks.
Have a great day.
You too.